Did you know that in Earth's history, there was a time when 96% of all marine life disappeared? The skies were filled with ash, and the oceans lost their oxygen. And yet in the middle of that collapse, the first small reptiles began to emerge. Within only a few million years, they evolved into gigantic dinosaurs that would come to dominate the entire planet. Why were they the ones that survived while millions of other species vanished? This is the age of reptiles, the mysterious rise of the first rulers of Earth. Around 252 million years ago, one of the largest volcanic systems in Earth's history began to awaken, the Siberian Traps. This was not a single eruption, but a chain of volcanic activity that continued for hundreds of thousands of years, spreading across more than 7 million square kilometers. An area nearly the size of a continent constantly being melted from deep within the Earth. Each eruption injected enormous amounts of carbon dioxide and sulfur dioxide into the sky. Carbon dioxide accumulated like a massive thermal blanket, surrounding the planet, causing global temperatures to rise rapidly by an estimated 8 to 10 degrees C. At the same time, sulfur dioxide generated widespread acid rain that devastated vegetation and triggered the collapse of food chains from their very foundations. But even that was not the end. Deep beneath the oceans existed what scientists describe as a climate bomb, methane hydrate. As ocean temperatures increased, vast amounts of methane were suddenly released. Once it escaped into the atmosphere, Earth entered a state scientists call a runaway greenhouse effect, a self-amplifying feedback loop that could no longer be stopped. According to geological studies, nearly 96% of marine species disappeared, while 70% of life on land ceased to exist. This was no longer simply an extinction event. It was the complete restructuring of Earth's entire ecosystem. But within that chaos, not everything vanished. One small branch of life, almost insignificant in the old world, endured. They were not the strongest creatures. They were not the dominant rulers of the planet. Yet they possessed something else, the ability to adapt in a world that had just been erased. These were the archosaurs. And the question remains, why were these seemingly vulnerable creatures the ones that survived the final planetary reset? Anatomical studies revealed that archosaurs possessed a series of remarkable biological traits. The first was an upright leg structure positioned directly beneath the body, rather than the sprawling limb posture seen in many ancient reptiles. This allowed them to move more efficiently and conserve energy in a world where food had become dangerously scarce. The second was a more advanced respiratory system, built around a one-way airflow structure, a feature that would later become highly developed in dinosaurs and modern birds. This gave them the ability to absorb oxygen far more efficiently in the oxygen-depleted atmosphere that followed the catastrophe. The third was their rapid growth rate and shorter reproductive cycles, allowing populations to recover more quickly in environments that remained unstable and constantly changing. What makes archosaurs especially remarkable is that they were not a single uniform group. They split into multiple evolutionary branches. Some became the ancestors of dinosaurs. Some evolved into crocodiles. Others transformed into pterosaurs, the first vertebrates capable of powered flight, and much later into modern birds, a single lineage that would eventually shape the entire future of Earth's ecosystems. But at that moment in time, they were only small creatures living in the shadows of a planet that had just been rebuilt from collapse. Archosaurus could endure low oxygen environments, violent climate instability, and ecosystems trapped in continuous disruption. They did not require a stable world in order to survive. Yet this world would not remain in chaos forever. As the continent slowly drifted and merged into a massive supercontinent known as Pangea, Earth entered an entirely new phase, a planet without separating oceans, without stable climates, and without fixed ecological regions. And it was at that moment, from these small survivors, that an entirely new era began to emerge. After the Permian-Triassic mass extinction, Earth's tectonic plates continued to shift and collide, eventually merging into a colossal supercontinent, Pangea. It was a planetary structure that was almost without natural borders. Nearly all of Earth's landmasses fused into a single enormous body stretching from one pole to the other. According to modern geological models, Pangea existed roughly between 335 and 175 million years ago, covering nearly all of the planet's land surface during that time. The first thing to disappear was the oceanic separation between continents. The familiar marine barriers were gone, allowing life forms to travel thousands of kilometers without ever encountering a sea. But this immense connection also created a planet with an extreme climate unlike anything before. In the center of Pangea, the regions farthest from the oceans, temperatures rose dramatically due to what scientists call the continentality effect. Ancient climate studies suggest that many areas may have reached brutal temperatures above 40 to 50 degrees C during dry seasons, only to shift suddenly into cold and arid conditions during other periods. Dust storms lasting for months, even years, have been identified through ancient sedimentary records. Planet-wide wildfires emerged as hot, dry climates combined with highly flammable vegetation such as ferns and ancient gymnosperms. Earth was no longer a stable world designed for life, but a planetary system trapped in constant instability and fluctuation. But Earth did not stop there. As the climate gradually became more stable and moisture levels increased, the planet began to enter an entirely new chapter, the Jurassic period. Forests expanded across vast regions. Ecosystems rapidly diversified, and the size of living organisms began to increase on a scale never seen before. From the small survivors that endured the harsh world of Pangea, a new era was preparing to erupt, an age in which Earth would not simply change, but begin evolving according to entirely different biological limits. Amid an Earth filled with dust storms, extreme climates, and unstable ecosystems, the first creatures that would eventually be called dinosaurs began to appear. Around 230 million years ago, near the end of the Triassic period, the earliest fossils, such as Dinosaurs, Raptor, and Herrerasaurus, began to emerge within the geological record. Some scientists believe that Dinosaurs may have been one of the oldest dinosaur forms ever discovered, living approximately 243 million years ago. Most early dinosaurs measured only between 1 and 4 ft in length. They were lightweight, fast-moving creatures that primarily survived as opportunistic hunters or omnivores. Meanwhile, the world still belonged to many other giant reptilian groups, such as Rhesuchians, massive predators protected by armored bodies and equipped with bite forces far more powerful than those of the first dinosaurs. These enormous reptiles required tremendous amounts of energy to survive. The moment climate shifted or food sources declined, they became the first to suffer. Dinosaurs were different. Their smaller bodies required less energy. They grew quickly, reproduced rapidly, and adapted far more effectively to unstable environments. Research from the American Museum of Natural History suggests that early dinosaurs possessed an upright posture beneath the body, rather than the sprawling stance common among many ancient reptiles. In addition, their lightweight skeletal structures and higher metabolic rates allowed them to respond more rapidly to environmental change, an advantage that helped them outlast many of their competitors. As numerous large reptilian groups gradually declined under constantly changing environmental pressures, dinosaurs began adapting to a wide range of habitats, from the scorching dry interiors of Pangea to the more humid river regions. Slowly, they occupied the ecological gaps left behind by collapsing species. And then another catastrophe arrived. Around 201 million years ago, Earth entered the end Triassic extinction event. Once again, the planet changed, and this time the ecological void that opened was larger than ever before. If the Triassic period was the age of survivors, then the Jurassic period was the moment Earth began to breathe again. Between roughly 201 and 145 million years ago, Earth's climate shifted into a significantly warmer and more humid state. Geological models indicate that atmospheric carbon dioxide levels during this period were several times higher than today, estimated to range between 1,000 and 2,000 parts per million, creating a natural greenhouse effect that maintained stable global temperatures. Life exploded across the planet. Forests covered the continents with a density never seen before. Plant systems such as ferns, conifers, and ancient cycads flourished, forming complex three-layer ecosystems. Earth now resembled a green world slowly being filled back in after millions of years of chaos. Within that environment, dinosaurs evolved in an entirely new direction: gigantism. This was the age of the creatures known as sauropods, the true giants of the land: Brachiosaurus, Diplodocus, Torch, and Argentinosaurus. Some species exceeded 30 to 35 mm in length and weighed dozens of tons. Their hollow, bird-like bone structures reduced body mass while maintaining immense strength. Their air sac respiratory systems allowed one-way airflow, dramatically increasing oxygen exchange efficiency beyond that of traditional reptiles. And within the same ecosystem, another balancing force emerged: predators. Species such as Allosaurus, Ceratosaurus, and later Tyrannosaurus rex represented the peak of the food chain. The Jurassic period was also a world defined by violent balance. It was an ecosystem constantly adjusting itself, where no position remained permanently safe. But what makes the Jurassic even more extraordinary are fossil discoveries from China, including species such as Microraptor and Einchiornis, which revealed that many dinosaurs possessed feathers. In reality, dinosaurs share a direct evolutionary connection with modern birds. According to research published by Nature, birds are the direct descendants of a branch of theropod dinosaurs. The skies also belong to giants. Pterosaurs, with wingspans reaching 10 to 12 mm, became the first actively flying creatures to achieve such enormous size. And beneath the oceans, species such as ichthyosaurs and plesiosaurs developed unusual reproductive strategies, giving live birth directly in the water, instead of laying eggs like many other reptiles. This reveals an important truth. Dinosaurs and their relatives did not simply adapt to life on land. They expanded across the entire biosphere: the skies, the surface, and the oceans. But when an ecosystem reaches the height of stability, that is often the moment it begins moving toward its greatest turning point. Between roughly 155 and 66 million years ago, terrestrial ecosystems began developing far more defined food chain structures. Tyrannosaurus rex emerged as the final endpoint of biological energy flow. These creatures were not simply carnivores, but biological machines optimized for a single purpose: controlling the movement of life throughout the ecosystem. T. rex, in particular, which lived near the end of the Cretaceous period around 68 to 66 million years ago, possessed one of the most powerful bite forces ever recorded on land, estimated between 35,000 and more than 57,000 newtons according to biomechanical studies. To put that into perspective, this bite was powerful enough to crush the bones of most contemporary animals in a single attack. And it was precisely the existence of these predators that created something essential: ecological balance through violence. Without predators, herbivore populations would explode uncontrollably and destabilize the entire ecosystem. The existence of predators such as Allosaurus or T. rex was therefore not simply dangerous, but a necessary part of preventing ecosystems from collapsing under their own imbalance. But what made the Jurassic and Cretaceous worlds even more extraordinary was the scale of everything. This was a conflict between giants, where every hunt became a biological event filled with extreme risk. A single mistake could mean death. In such an environment, life was no longer a stable condition, but a continuous chain of survival decisions made in fractions of a second. These creatures expanded across the skies through pterosaurs and into the oceans through species such as ichthyosaurs and mosasaurs, creating a global ecosystem no limited by habitat boundaries. Between roughly 266 million years ago, the planet became dominated by ancient reptilian lineages across all three major environments: land, air, and sea. This is an extraordinarily rare achievement in evolutionary history. Very few groups of organisms have ever reached such a complete level of adaptation. In the skies, creatures belonging to the group known as pterosauria began to appear. They represented an entirely separate evolutionary branch and became the first vertebrates to achieve true powered flight. Some species, such as Quetzalcoatlus, possessed wingspans ranging from 10 to more than 12 m, comparable to the length of a modern light aircraft. But the skies were still not the final frontier. Beneath the oceans, another world operated in parallel. Marine reptile groups, torture such as ichthyosaurs and mosasaurs, became the dominant predators of the ancient seas. What makes them especially fascinating is that their ancestors originally lived on land, but after millions of years of evolution, they returned to aquatic environments and developed characteristics strikingly similar to modern fish or dolphins. Ichthyosaurs possessed streamlined bodies, extremely high swimming speeds, and enormous eyes adapted for the dim conditions of deep marine environments. Some fossil evidence suggests they exceeded 15 m in length. Meanwhile, Mosasaurus evolved into one of the most terrifying predators of the late Cretaceous period oceans, equipped with conical teeth and a bite force powerful enough to crush massive prey. Remarkably, multiple fossil discoveries suggest that mosasaurs gave birth directly in the water, instead of returning to land to lay eggs. Because when an ecosystem reaches such a level of global interconnectedness, a single catastrophic event can cause the entire system to collapse at once. And that event was already racing toward Earth from space. Around 66 million years ago, Earth faced one of the most violent moments in the history of life. It was a collision that happened almost instantly, yet carried enough force to redirect the entire evolutionary path of the planet. Torch, an asteroid measuring roughly 10 to 12 km in diameter, struck the region, now known as the Yucatan Peninsula, Mexico, at a speed exceeding 20 km per second. The impact created the Chicxulub crater, nearly 180 km wide, and released energy equivalent to billions of nuclear bombs. According to data from the NASA Earth Observatory and the U.S. Geological Survey, shock waves spread across the planet within the first few minutes. Massive earthquakes erupted on a global scale. Heat generated by debris re-entering the atmosphere ignited forests thousands of kilometers away almost simultaneously. Billions of tons of dust, sulfate, and fragmented rock were blasted into the stratosphere, forming a planetary veil that blocked the sky for months, perhaps even years. Sunlight disappeared. Global temperatures dropped rapidly. Food chains collapsed from their lowest levels upward. The giant creatures that had dominated Earth for more than 160 million years began to vanish. Truchy snorts and sighs, Trinon, avian dinosaurs, pterosaurs, and many large marine reptiles could not adapt quickly enough to such an abrupt transformation. Size had once been an advantage. Now it became a burden. Massive bodies required massive amounts of energy. Once vegetation died and prey populations disappeared, entire large-scale ecosystems collapsed through a domino effect. But not everything came to an end. Some smaller organisms survived: primitive mammals, burrowing species, and most importantly, a small branch of feathered theropod dinosaurs. Dinosaurs did not vanish entirely. A part of them continued to survive, flying across the skies of the New World. And that leads to the final question. If birds are the direct descendants of dinosaurs, did the age of dinosaurs truly end? The dominance of dinosaurs did not emerge from pure strength alone, but from an extraordinary ability to adapt to a planet in constant transformation. Rising from the ashes of earlier mass extinctions, they established a biological empire that endured for more than 160 million years, a span of time far greater than the entirety of human history. Today, within every heartbeat and every wing beat of the birds crossing our modern skies, the bloodline of those ancient rulers continues to flow silently onward. Dinosaurs did not disappear. They transformed, becoming part of an eternal legacy, a living testament to the resilience and unstoppable persistence of life on Earth. Chorka laughter, chor for decades. Mammals from the age of dinosaurs were reconstructed from little more than a few fossilized teeth, a fragment of a jawbone, or occasionally a shattered piece of skull. From this limited evidence, science arrived at what seemed like a reasonable conclusion. Mesozoic mammals were small, simple creatures living in the shadows of gigantic dinosaurs. But in 2003, within ancient lake deposits in northern China, paleontologists uncovered a nearly complete fossil preserved in fine, grained rock laid down in calm, still water. Isotopic dating placed the age of the sediment at approximately 164 million years ago in the Middle Jurassic. What shocked researchers was not only its age, but the form of the creature preserved inside. This animal measured at least 42.5 cm in body length, with an estimated mass of around 800 g, far larger than the traditional image of a dinosaur, age mammal. Its body was covered in fur, a defining mammalian trait indicating that advanced temperature regulation had already evolved. Torchy size and snorts, torch yet. The most striking features lay in the limbs and tail. The limbs bore membranes stretched between the digits, while the tail was flattened horizontally, shaped like a paddle. The creature did not belong to any modern mammalian group. It was classified as a mammaliaform, an evolutionary grade close to true mammals, positioned along the branch that would eventually lead to them. Its existence demonstrated that as early as the Jurassic, while dinosaurs dominated the land, mammalian ancestors had already entered complex ecological niches, including aquatic environments. Before this discovery, a semi-aquatic lifestyle in mammals was thought to have emerged much later, roughly 100 million years afterward, among lineages more closely related to modern mammal. The 2003 fossil pushed that timeline back by over 100 million years, overturning how we understand both the speed and the scope of Mesozoic mammal evolution. If a mammaliaform possessed fur, swimming membranes, and a paddle-like tail 164 million years ago, then these traits were being tested remarkably early. In a world defined by intense competition and ecological pressure, small animals living in dense forests, swamps, or along riverbanks have a far lower chance of fossilization than giant dinosaurs roaming dry plains. Why, after the catastrophe at the end of the Cretaceous, did only a handful of lineages survive and flourish, while many other evolutionarily rich branches vanished from history? The answer lies in what happened afterward, across a chain of ecological transformations that unfolded over tens of millions of years. For nearly a century, the dominant image of mammals in the age of dinosaurs portrayed them as tiny, mouse-like creatures, weighing only a few dozen grams, living furtively at night, and surviving by feeding on insects. For most of the 20th century, what scientists uncovered about Mesozoic mammals consisted mainly of teeth and jawbones. These are the hardest parts of the skeleton and the most likely to fossilize. In contrast, delicate limb bones, slender vertebrae, and soft tissues were rarely preserved. From isolated teeth, science was forced to infer body size, lifestyle, and ecological roles. Those teeth suggested that most Mesozoic mammals were indeed small, with many species weighing only tens to a few hundred grams. In modern ecosystems, animals of that size can be predators, ecosystem engineers, or regulators of insect populations. But from the late 20th century into the early 21st, new discoveries began to accumulate piece by piece in China, Mongolia, and North America. These regions contained fine, grain sediments and ancient environments well suited to preserving small animals. The new fossils revealed the existence of cat-sized predatory mammals with body lengths exceeding 1 m, sharp teeth, and powerful limbs capable of hunting small reptiles, lizards, and even juvenile dinosaurs. Other species showed four-limbed structures and claws, indicating exceptional climbing ability adapted to life in the forest canopy, where large dinosaurs struggled to reach. Still, others possessed short, robust forelimbs and thick claws clearly suited for digging and a subterranean lifestyle. What matters most is this: all of these lifestyles existed at the same time within and same geological periods. This shows that Mesozoic mammals had already diversified extensively, clearly partitioning resources and ecological niches. Modern science no longer relies on a few bone fragments alone. It integrates morphology, biomechanics, bone microstructure analysis, and ecological comparisons with living animals. These analyses reveal that many Mesozoic mammals had high metabolic rates, the ability to maintain stable body temperatures, and considerable behavioral flexibility. Looking back, it is true that many Mesozoic mammals were small and active at night, but night was not absolute darkness. It was its own ecological arena, governed by different rules, chor, where large size was no longer an unquestioned advantage. If Mesozoic mammals were already so diverse and successful, what prevented that evolutionary radiation from continuing into the present? The answer lies within the complex world of the Jurassic, where mammals were no longer merely shadows of dinosaurs, but active participants in a dynamic and competitive ecosystem. It unfolded quietly, yet profoundly, between roughly 201 and 145 million years ago. While dinosaurs dominated open landscapes and daylight hours, the world of Jurassic mammals expanded in multiple dimensions, underground, in the trees, through the air, and even into aquatic environments. Jurassic mammaliform fossils reveal a remarkable degree of ecological diversity. Some species were clearly adapted for digging, with short forelimbs, robust bones, and powerful shoulder joints that allowed them to burrow into soft soils or riverbank sediments. These burrows were not only shelters from predators, but also stable environments in terms of temperature and humidity, a major advantage in the fluctuating Jurassic climate. In another ecological layer, within dense Jurassic forests, where towering conifers and tall ferns formed thick canopies, tree-dwelling mammals could access abundant food sources such as insects, eggs, and young fruits, while avoiding many predators on the forest floor. Some mammaliforms went even further, as fossils show the presence of stretched skin membranes between the forelimbs and hind limbs, similar to the gliding mechanism of modern flying squirrels. This was not powered flight like that of modern bats, but it was sufficient to glide from tree to tree, conserving energy and greatly expanding their living range. And then there were species that chose a far less expected path. Life in the water, semi-aquatic Jurassic mammaliforms possessed horizontally flattened tails, webbed limbs, and flexible spines, allowing efficient swimming in lakes and swamps. With body lengths exceeding 40 cm and masses approaching 800 g, they were far from small or fragile creatures. During the Jurassic, mammals did not compete head-on with giant dinosaurs on open plain. Instead, they expanded vertically, and laterally within their environments. What stands out is that this radiation occurred simultaneously across multiple lineages, rather than along a single evolutionary path. Morphological studies also indicate that many mammalian forms had highly specialized forelimbs, with clear functional separation between locomotion, gripping, digging, or swimming. Flexible joints allowed wide ranges of motion, while bone structures reveal strong load-bearing capacity. This stability allowed evolutionary branches to specialize deeply, experimenting with new survival strategies without being repeatedly disrupted by global catastrophes. Between approximately 175 and 145 million years ago, mammalian diversity reached its highest level across the entire Mesozoic era. Yet, it is precisely here that a paradox begins to emerge. When so many lineages had become this successful, what happened when competitive pressures intensified? Not only from dinosaurs, but from other shadow-dwelling mammals themselves. When we think of the Mesozoic era, the image that usually comes to mind is one of massive open competition, giant dinosaurs clashing across vast landscapes. But running in parallel was another struggle, far less visible. A competition in the shadows, where Mesozoic mammals faced not only dinosaurs, but entire ecosystems that had already been claimed long before they arrived. Mesozoic mammals rarely competed directly with large carnivorous dinosaurs. The difference in size and strength made such encounters almost hopeless. As dinosaurs dominated open spaces during daylight hours, they reshaped the entire ecological structure. From food availability and movement patterns to the daily rhythms of smaller animals, the most obvious strategy mammals adopted was nocturnal activity, as evidence from eye socket structure. Optic nerves and inner ear anatomy in many mammalian forms reveals highly developed hearing and vibration sensing, while sharp daytime vision was not a priority. Night activity allowed mammals to avoid most daytime dinosaur predators, while granting access to insects and small animals that were also active under the cover of darkness. But dinosaurs were not the only competitors. In the skies, pterosaurs ruled the air, controlling flying insects and small fish along shorelines. In rivers and wetlands, ancient crocodilians, with their semi-aquatic bodies, powerful jaws, and rapid reflexes, were formidable predators. Even in environments that might seem safer, burrows, dense forests, swamps, Mesozoic mammals still competed with one another as their numbers and diversity increased throughout the Jurassic. A snort's a torture. This competition came down to who was better suited to extremely narrow ecological niches, where a burrowing species had to dig faster, deeper, and more efficiently to secure shelter and escape predators. A tree dweller needed superior grip and agility to avoid being displaced from food sources. A semi-aquatic mammal had to strike a perfect balance between swimming and movement on land. Mesozoic mammals became exceptionally skilled in highly specific roles. But that specialization came at a cost: deep dependence on stable environments. Forests needed to remain dense, wetlands expansive, and insect populations abundant when everything functioned smoothly. This shadow ecosystem was efficient and resilient. Yet competition did not come only from the environment. It also came from evolutionary speed. Mammals with more flexible strategies, omnivorous diets, varied movement, and adaptability to multiple habitats tended to expand their ranges more successfully. From an evolutionary perspective, this was a massive experiment, one in which mammals tested every possible survival strategy in a world ruled by others. And as the Cretaceous period approached, Earth began to lose the relative stability it had enjoyed during the Jurassic. Climate fluctuations, shifting vegetation, and ecological restructuring started to place pressure on species that had become too perfectly adapted to the old world. That slow building stress marked the beginning of a crisis that unfolded long before the end. Cretaceous asteroid ever struck. During the Mesozoic era, mammals evolved along many different evolutionary paths. But when scientists examined the fossil record, they realized that teeth are the most frequently preserved body parts and the richest sources of information. From thousands of these tiny fossilized teeth, a much larger picture gradually emerges. The success or failure of mammalian lineages depended less on where they lived and far more on what they could eat and how quickly they could change their diet. Among Mesozoic mammals, multituberculates stand as a classic example of long-term success followed by a tragic ending. This group appeared around 160 million years ago and survived for nearly 130 million years, making it one of the most successful mammal lineages ever to exist. Their teeth featured rows of multiple small cusps, highly effective at grinding tough plant material such as seeds, young stems, and coarse vegetation. Yet, that very dental structure also locked multituberculates into a narrow evolutionary path. Their multi-cusp teeth worked well for plant-based diets, but proved inefficient when flexibility became necessary. At the same time, another truly revolutionary evolutionary direction emerged: tribosphenic teeth. This dental design combined three functions in one: cutting, piercing, and grinding. Each tooth had sharp edges for slicing meat, pointed cusps for piercing, and broad surfaces for crushing food. Tribosphenic teeth allowed mammals to become true omnivores in a world entering a prolonged period of instability, and that flexibility was a matter of survival. From this evolutionary pathway arose the two most important branches of modern mammals: marsupials and placental mammals. Notably, as environments fluctuated, it was species with flexible dental structures that maintained stable populations. This revolution in the mouth reveals a fundamental lesson of evolution. Adaptability does not lie in strength, but in versatility. A single tooth capable of handling many kinds of food opened the door to an entire evolutionary future. As the Cretaceous period continued to unfold, the world was changing not only in climate, but also in the very structure of ecosystems. And it was within this context that the stage was set for a global-scale ecological revolution in which flowering plants, insects, and mammals together reshaped the Earth. Around 125 million years ago, Earth entered a period of profound yet quiet transformation. The Cretaceous was not only the final age of the dinosaurs, it was also the era that completely reshaped the relationships among plants, insects, and mammals. At the center of this revolution were flowering plants. Early in the Cretaceous, they made up less than 5% of terrestrial vegetation. Most of the planet was still dominated by ferns, cycads, and ancient conifers. By the end of the Cretaceous, however, that figure had surpassed 80%, turning flowering plants into the dominant life form on land. Flowering plants reproduced faster, displayed far greater morphological diversity, and most importantly, formed tight, mutually beneficial relationships with pollinating insects. As flowers spread across the continents, insects exploded in both number and diversity. Beetles, bees, to ants, flies, and butterflies flourished, creating a new food resource that was richer and more stable than ever before. Terrestrial ecosystems no longer relied primarily on coarse vegetation and slow energy cycles, but shifted toward a dynamic, multi-layered system filled with dense interactions. It was within this environment that small, flexible mammals began to gain a clear advantage. The Cretaceous climate also evolved in ways that supported this transition. Global temperatures were generally warmer than today, with no permanent polar ice. Rainfall increased, especially in tropical and subtropical regions. Dense forests expanded, gradually replacing the drier and simpler ecosystems that had dominated earlier periods. These environments were unfavorable for highly specialized species or those dependent on open spaces, but ideal for small, agile organisms capable of hiding easily and exploiting a wide range of food sources. For Mesozoic mammals, this marked a turning point. Larger, highly specialized species, or those dependent on a single type of food, began to struggle. In contrast, small, omnivorous mammals with flexible activity patterns in time and space became increasingly stable. Tribosphenic teeth, which had evolved earlier, now became a strategic advantage in this new world. They allowed mammals to exploit insects, toss off fruits, young seeds, and even small carcasses, energy, rich resources that became abundant in the transformed ecosystem. Crucially, this revolution did not immediately eliminate older mammal lineages. Multituberculates, semi-aquatic mammalia forms, and ancient tree-dwelling mammals continued to persist for tens of millions of years. For dinosaurs, the Cretaceous remained a golden age for many major groups. Mammals did not compete head-on. Instead, they quietly expanded their ecological roles. The Cretaceous ecological revolution was therefore a long-term process of preparation. And it was from this foundation that the most decisive moment, the KPG catastrophe, acting as a ruthless biological filter, completed the transformation that the Cretaceous had set in motion. Around 66 million years ago, Earth entered a moment that humans would later call the KPG boundary. In a brief geological instant, a celestial body roughly 10-12 km in diameter slammed into what is now the Yucatan Peninsula, creating the Chicxulub impact crater about 180 kilometers wide. The energy released was equivalent to billions of nuclear bombs, enough to shake the entire planet. But the most important thing to understand is this: the asteroid did not simply wipe out all life. It triggered a long chain of reactions, turning the event into a harsh biological filter, rather than an immediate end. In the first hours after the impact, Earth plunged into chaos. Shock waves spread across the continents. Global wildfires erupted as superheated debris fell back through the atmosphere. Dust, sulfur, and aerosols were blasted into the upper atmosphere, blocking sunlight. Surface temperatures initially spiked, then dropped sharply for years, creating what is commonly called an impact winter. Photosynthesis nearly came to a halt, but not all life died instantly. Fossil evidence shows that many mammals survived the initial shock. They were not destroyed at the moment of impact, nor did they disappear immediately when the dinosaurs collapsed. What killed most Mesozoic life was not the explosion itself, but the prolonged collapse of ecosystems that followed. As plants died in mass from the lack of light, food chains broke down from the base. Herbivores declined rapidly. Large carnivores, which required stable food supplies, vanished within just a few generations. Meanwhile, small organisms with low energy needs, capable of omnivore or hiding, showed significantly higher survival rates. This was the moment when survival strategies developed during the Jurassic and Cretaceous truly proved their value. Small mammals living in burrows, along riverbanks, in swamps, or in semi-aquatic environments held a distinct advantage. Underground temperatures were more stable. Food sources, such as insects, carrion, roots, and leftover seeds continued to exist in the darkness. Species dependent on a single food type or a narrow habitat began to disappear. Not over days, but over hundreds of thousands to millions of years in the early Paleogene. This is the key point that is often misunderstood. The KPG was not a sharp line where everything before died and everything after lived. In reality, many Mesozoic mammal lineages persisted after the impact event. Multituberculates continued to survive for tens of millions of years. Some ancient mammalia forms still appear in the early Paleogene fossil record. Each climate shift, each change in vegetation, and each small break in the food chain eliminated more inflexible lineages. Species with tribosphenic teeth, omnivorous diets, fast reproduction, and broad ecological ranges began to dominate. They already existed, quietly refined through tens of millions of years of competition in the shadows. The catastrophe merely exposed the differences between survival strategies. Dinosaur lineages had vanished forever. Many new branches emerged, while many others continued to disappear. The disappearance of most Mesozoic mammal lineages was not simply an ending, but a harsh trial imposed by evolution and global geological upheaval. For millions of years, living in the shadow of dinosaurs, these creatures carried out bold biological experiments, laying down some of the earliest ecological links. Most species failed to pass through this historical bottleneck, leaving behind only scattered fossil fragments, locked within layers of rock. But that brutal filtering process also cleared ecological space, setting the stage for an unprecedented burst of diversification. The survivors were not necessarily the strongest, but the ones best suited to a fractured and unstable world. The story of these lost mammals stands as proof of an enduring rule of nature. Across the flow of time, the fall of an old dynasty becomes the seed for the rise of new ones, including, ultimately, our own. Thank you for staying with WOFO Space until the very end of this journey through the vast universe. If you found this video interesting and insightful, don't forget to like, share, and subscribe to WOFO Space so you won't miss our next cosmic adventures. Your support means the world to us and fuels our passion to keep exploring the wonders beyond.